So recall that the execution order of iterations depends on the order in which we represent our loop iteration variables. So the execution order is the ascending lexicographic order of the loop iteration space. Now, what if I wanted to change the execution order or rewrite the loop such that the execution order changes, right? So that's a question that we're going to try to address in this lecture module. What if we want to change the order? And I'm going to assume here that when we do this, when we change the order, we are respecting the dependencies. Maybe there are no data dependencies across different iterations of the loop nest, in which case it's okay to change the order any which way. In some cases, it may be possible that there are data dependencies, yet it may be possible to change the order such that the data dependencies are respected. What are the possible ways in which we can potentially change the execution order is something that we're going to discuss in later modules. But let's say we know that it is possible to change the execution order. Then what is the algorithm, or how does one go about changing the execution order? That's the discussion that we're going to have in today's module. So here's an example. Let's say my loop nest is for I equals 0 to n. For j equals I, j is less than 7 and j is less than I plus 4. Recall that I can have multiple inequalities in my convex polyhedron, and so this is j is less than 7 forms one upper bound and j is less than I plus 4 forms an other upper bound. And then you say j plus plus, and then there is some body. In this case, I've deliberately chosen a body where there are no data dependencies across different iterations of this loop nest. Now, if I was to pictorially draw the iteration space, it would look something like this. This particular line here is basically I equals j, and notice that because the lower bound of j is I, so everything on the left of this particular line represents j is greater than or equal to I. Similarly, we want j is less than I plus 4, so that's just a parallel line going from 3, starting, just at I. This is just j is equal to I plus 3. And then everything on the right of this is basically j is less than or equal to I plus 3, or j is less than I plus 4. And then there is also j is less than 7 is another upper bound. And so everything marked with yellow in this particular polygon, convex polygon, is basically the iteration space. All the points in this convex polygon represent the iteration space. Now, the point that I want to make here is that this is the iteration space, and the order in which this iteration space is being traversed by the current loop nest is that it first goes 0, 0, then it says 1, 0, and then 1, 1, and then 2, 0, 2. Because recall that I is the x-axis and I is the first index of my loop iteration vector, and so it's going to go this, then 1, 1, 0, 1, 1, then 2, 0, 2, 1, 2, 2, then 3, 0, 3, 1, 3, 2, 3, 3, and so on. What if I wanted to switch the order of execution, or switch the order of iteration over this iteration space? And in that case, maybe I want to switch the axis such that it goes in the vertical direction first. So it goes 0, 1, 0, 0, 1, 0, 2, 0, 3, 0, 1, 1, 2, 1, 3, 1, 4, 1, and so on, right? So it's basically vertical first order in this particular diagram. Now, if I want to do that, and once again, I'm assuming that it's okay to do that, assuming there are no data dependencies that are getting violated by doing this. The question is, if I want to do that, how should I rewrite my loop so that it still captures the same convex polyhedral space and yet captures, changes the execution order or the iteration order of this space? In this example, I'm going to discuss how to switch axes I and j. So here is the solution. I'm going to have the outer loop to be j, of course, that's what I wanted, and the inner loop to be I. But the important question here is, what should be the minimum lower bound and the upper bound of j, and then what should be the minimum lower bound and upper bound of I. Recall that in the original loop, lower bound of I was 0 and the upper bound of I was 9. And because j was the inner variable, j's lower bounds and upper bounds could be specified as functions of I. Now, when I switch the order, then j's lower bounds and upper bounds need to be constants, and i's lower bound and upper bounds can be functions of j. Okay, so now question is, how do I figure out what the upper bounds and lower bounds should be? And here I give you the solution. So for j equals 0 to 6, how do I know that j needs to traverse from 0 to 6? Notice that this is the space from 0 to 6 for which the polyhedral space has a projection on J. Alright, so I'm using the word projection. It basically means what are all the possible values of J for which the polyhedral space has a non-zero element when you kind of expand from J in the direction of I. And then for every value of J, I have a lower bound and an upper bound of I. So for example, at this particular value of, let's say for at value 2 of J, I can range from 0 to 2. At value 5, I can range from 2 to 5 and so on. So that's the lower bound and upper bound that I need for I given a fixed value of J. And I'll give you the solution, and later we're going to discuss what the algorithm to get the solution is. I's lower bound is maximum of J minus 3 and 0. So I is greater than equal to both J minus 3 and 0, and I is less than equal to J. So upper bound is J and lower bound is J minus 3 comma 0. So how do I get from here to the solution, from the original loop to the loop with the switched axis? How do in particular, how do I understand, how do I know these lower bounds and upper bounds of I and J? That's the question that I'm going to answer in this particular lecture module. So I'm going to first identify what are all the potential values of J. And this is done by projecting the convex polyhedron on the J axis, just like we discussed in the figure below. A figure in the previous slide, we just project the convex polyhedron on the J axis to see where all it casts the shadow, so to say. In other words, what are all the values of J for which the convex polyhedron has a non-zero set of points. And then for each value of J, identify potential values of I. So for each value of J, draw a line and figure out what are the points in the convex polyhedron that will lie on that particular line. And this itself must be expressible as a convex polyhedron on I. Notice that in a one-dimensional space, a line segment is a convex polyhedron for a 1D space. But in general, I mean, I'm using the example of a 2D space where I'm projecting on one first and then everything that remains. But in general, if I if I just take one dimension out and project on it, and then try to figure out what is the space for the rest of the iteration variables, the rest of the dimensions for a fixed value of the first value, the projected out loop iteration variable, in this case J, then I'm guaranteed to get a convex polyhedron on I. And this is just a property of convex polyhedra, all right? And that's the reason we kind of restrict ourselves. These are some of the reasons we restrict ourselves to convex polyhedra, because they have such nice properties. What is the property? If you project a convex polyhedron on one of the axes, that basically means that you get a new convex polyhedron that has all the axes except that one axis, and this is a good property to have. Okay, so here is the definition, a formal definition of projection. Let S be an n-dimensional polyhedron. The projection of S onto the first m dimensions. So let's say my n-dimensional polyhedron had dimensions x1, x2, x3, x4 all the way till xn. But I want to project on the first m dimension I'm arbitrarily chosen the first m dimension, so any m dimensions, and let's call them x1, x2, xm without loss of generality, such that for some of the other dimension values, xm plus 1, xm plus 2, xm plus 3 xn, for some value, so I can choose any value I like for the other dimensions, the full vector x1, x2 xm, xm plus 1 xn, which is represented by this, is in S. In other words, what are some values in the projected in the m dimensions here? What are some values in the m dimensions here for which there is some value for the other dimensions? In this case, in this case, m is the jth dimension, and everything else is represented by the ith dimension. So what are some values of J for which J comma I belongs to, for some value of I, J comma I belong to S, alright? So for example, this particular point here does not belong to the projection of S, right? So this point here does not belong to the projection of S because there is no value of I for which j comma I, for this, let's say this value was, let's say 10. So there's no value of I for which 10 comma I belongs to S. And so 10 does not belong to the projection of S on J. Okay. Whereas if I look at, for example, 5 or 3, then there are some values of I for which 3 comma I belongs to S. And so 3 will belong to the projection of S. So in other words, once again, the projection is basically all those points x1 dot 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 xm such that for some values of the other dimensions, the entire vector x1 dot 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 xn which includes xm x1 dot 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 xm, and then for some values xm plus 1 dot dot xn is in S. Okay. So what's the algorithm to identify a projection of one polyhedron on one of the axes? So notice that in my previous definition I used first m dimensions. If I want to project on first m dimensions, maybe I can keep removing one dimension at a time. So for example, the first time I can remove the xnth dimension, and so I will get a projection on the first n minus 1 dimension. Then I can remove the n minus 1 dimension, and I will get the projection on the first n minus 2 dimensions until I reach m, in which case I will get a projection on the first m dimensions. So we're going to approach the problem similarly. We're going to try to project on one less dimension. So if I have a polyhedron of n dimensions, I'm going to try to project it on a polyhedron of n minus 1 dimensions by removing one dimension. And if I'm able to do this, then I'm also going to be able to solve my original problem, which is change the execution order. So how am I going to do that? Well, recall that my original polyhedron had, let's say, I and j. So if I want to first have j at the outer loop and I in the inner loop, what am I going to do? I'm going to first project on j. Alright, which means I'm going to remove I, and then I'm going to basically see what is the projection of j, and then from there I'm going to basically proceed, and now I have a new convex polyhedron which is on I, and that convex polyhedron, maybe I want to remove another dimension. In this case there's only one dimension, so basically a convex polyhedron in 1D space is nothing but a lower bound and an upper bound, and that basically can be used as the upper bound and lower bound of the inner loop. But if I had, let's say, 3 dimensions, then what I would have got after projecting on J would be a 2-dimensional polygon, convex polygon, and once again I can choose to project on one other axis, let's say I this time, and then I would get another 1D space which would be a lower bound and upper bound. And so in this way I can choose to have any order to visit my convex polyhedron. So we have reduced the problem of being able to switch axes to be able to project on dimensions, one less dimension. So remove one dimension and project it on the remaining dimensions. So we're going to do this, and so how are we going to do this? We want an algorithm which takes as input a convex polyhedron S on n dimensions, x1 dot dot xn, and we want one variable xm that needs to be eliminated so that we can project S on everything else except xm. And the output would be a projection of S on dimensions other than the mth, and we're going to call this new polyhedron S prime, and this is also going to be a convex polyhedron by the property of convex polyhedra. And here's the algorithm. We're going to have a representation for S, and recall that we already discussed the representation for S. S is basically all vectors x such that b times x, the matrix multiplication, plus a vector b is greater than or equal to 0. And this is a way to specify any convex polyhedron. And so I'm going to represent S using this representation. In this representation, x is a n-dimensional vector. And let's say C are all the constraints in S that involve xm. So some of these constraints in that come out of these equations are going to involve xm. By involve, I mean the coefficient of xm is non-zero, and some other constraints are not going to involve xm, which means they're in those particular constraints, xm, the coefficient of xm will be 0. And so I'm going to first focus on all these constraints that involve xm. The constraints that do not involve xm are already good enough for my S prime polyhedron because they already don't have xm, and that's what I wanted. I wanted to remove xm from these inequations, and so that I can have upper bounds and lower bounds on everything else except xm. And so things that already do not have xm, they're already good to be added to my solution, which is S prime. But for, and so that's what I do, and this is something that I've written at the end of the slide, but I just discussed earlier, is that let's add everything that does not belong to C, which means where the coefficient of xm is already 0 to S prime, and that would be my, that would be form a part of my projection S prime. But for the constraints that involve a non-zero coefficient for xm, identify, basically that's a system of equations. So C is nothing but a system of inequations, which has, each of those inequations has xm in it. So you bring them into a certain form, which is either you write them as L is less than equal to C1 into xm, where L can be some affine expression on all the variables except xm, and then you bring xm here, and here I'm assuming that C1 should be greater than equal to 0. So that's why it less than equal to C1 xm, or if or you should be able to bring it into this form, C2 xm is less than equal to u. Here L and u are arbitrary affine expressions on all the variables that x1 dot 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 xn except xm. Okay, so I should be able to bring all these inequations in this form, because after all they contain xm and they contain some other variables. So what I do is I bring all the other variables to one side and xm to the other side. I ensure that the coefficient of xm is positive, and so either I'm going to have an inequation of the form L is less than equal to C1 into xm, or I'm going to have an inequation of the form C2 into xm is less than equal to u, depending on whether the coefficient of xm was negative or positive for a certain inequality like greater than equal to. Okay, so once I get this, once I get all the inequations in C in this form, I look at every pair of such inequations and add C2L is less than equal to C1U. All right. So basically, mathematically this is very easy to see. If I just multiply this inequation with C2 and this inequation with C1, then what I get is C1 C2 xm here, and then C1 C2 xm here, and so I have two inequations, which is C2L is less than equal to C1 C2 xm, and C1 C2 xm is less than equal to C1U, and so from that I can just infer that C2L is less than equal to C1U. What have I done? This is just algebraic manipulation, but basically what I'm doing is I'm trying to identify the projection on everything except xm. So all the points that can potentially, firstly I want to capture all points such that S, for some value of xm, there is a non-zero set of points for some value of xm. In that case, that point should belong to S prime, and so this is what I get. I add C2L is less than equal to C1U, and I don't want to add any other points. I don't want to add points in S to S prime such that for which there is no value of xm such that the entire set belongs to S. And so this particular algorithm is called the Fourier Motzkin method. Fourier Motzkin method, based on the people who proposed this algorithm for the first time. So overall, once again, I first identify those equations which do not involve xm and simply add them to S prime. For those equations that involve xm, I bring them to either the first form, which is L is less than equal to C1 into xm, or the second form, which is C2 xm is less than equal to u. And for every such pair, so I'm going to have to do a pairwise analysis. For every such pair of for first and second, I do C2L is less than equal to C1U, and I get a bunch of constraints, and I add all those constraints to S prime, and whatever I get is my resulting projection S prime. Now let's look at an example to see this in action. So this is our original example. I is greater than equal to 0, I is less than equal to 8, or I is less than 9. J is greater than equal to I, and J is less than equal to 6 or less than 7, and J is less than equal to I plus 3. Okay, so these form are constraints for this particular polyhedron. I've just written the lower bound and upper bounds as my matrices B and D. For example, I have this the first row here says I is greater than equal to 0, right? So my vector is ij, my iteration space vector is ij, with I being first. Then my second one says minus I plus 8 is greater than equal to 0, which basically means I is less than equal to 8, and that's coming from this constraint that I is less than 9. Similarly, the third one says minus I plus j is greater than or equal to 0, which is just coming from j is greater than or equal to I, and that's minus I plus j is greater than or equal to 0 is nothing but j is greater than or equal to I. The fourth one is saying minus j plus 6 is greater than or equal to 0, which basically means j is less than or equal to 6. And the last one says I minus j is greater than I minus j plus 3 is greater than or equal to 0, which means I is greater than or equal to, or j is less than or equal to I plus 3. Okay, so these matrices basically exactly encode the polyhedron defined by the iteration space in this particular loop. And now I want to eliminate I. So my first question here is, which of these inequations involve 0 coefficient for I? So what are the first one involves the coefficient 1 for I, the second one minus 1, third is minus 1, fourth is 0. So this particular row here, we can just add it directly to S prime because it already does not have I. And what does this translate to? It just translates to the fact that j is less than or equal to 6. Now here are the remaining equations, which is apart from the one that just that comes from S minus C. Here is C. C is basically all the remaining rows, which is 1 0 minus 1 0 minus 1 1 1 minus 1. Basically all the rows for which the coefficient for I is non-zero, and these are the corresponding values for the small b vector. And from here we basically get these equations. I is greater than or equal to 0. I bring it into those forms, either C1x m is greater than or equal to L, or u is less than or greater than or equal to u, or L is less than or equal to C into x. In this case it becomes I is greater than or equal to 0, I is greater than or equal to j minus 3, I is less than or equal to 8, and I is less than or equal to j. And now we consider each pair. Alright, so for example, I consider pair 1 and 2, and from there I'm going to get an equation which says j minus 3 is greater than equal, not 1 and 2. I'm going to look at all the pairs which has L on one side and U on the other side. So I'm going to consider pair 1 and 3. Alright, so I'm going to consider pair 1 and 3. I'm going to consider pair 2 and 3. Then I'm going to consider pair 1 and 4 and consider pair 2 and 4. So for 1 and 4, I have I is greater than or equal to 0 and I is less than or equal to 8. What does that give me? It gives me 0 is less than or equal to 8. So this is coming from 1, 3. Similarly, 1, 4, I is greater than or equal to 0, I is less than or equal to j. That gives me 0 is less than or equal to j. Right? I'm just using the Fourier Motzkin method. Then I look at I is greater than or equal to j minus 3, I is less than or equal to 8. So that just gives me j minus 3 is less than or equal to 8. This is coming from the second and the third equations here. Right? And then I look at second and fourth, which gives me j minus 3 is less than or equal to j. Now notice that some of these inequations are trivial. For example, 0 is less than or equal to 8 is really giving us no information whatsoever. Similarly, j minus 3 is less than or equal to j is also not giving us any information whatsoever. So what are we left with? We are left with 0 is less than or equal to j and j minus 3 is less than or equal to 8, and we add both of them to S prime. In other words, we add j is greater than or equal to 0 and j is less than or equal to 11 to S prime. So these are the two constraints that we get from C, and recall that we had one constraint from S minus C, which was j is less than or equal to 6, if you remember. And overall we get j is greater than or equal to 0, j is less than or equal to 11, and j is less than or equal to 6. All three basically we basically mean that j is less than or equal to 11 becomes redundant, right? Because if j is less than or equal to 6, then obviously j is less than or equal to 11 because 6 is less than 11. And so finally we get j is greater than or equal to 0 and j is less than or equal to 6, and this forms our projection of the polyhedron on j. And so this also gives us the outer loop lower and upper bounds for j.